Okay, hello everyone. Thanks for joining us. Welcome to the webinar. We're going to be talking about fighting fraud with Amazon, Neptune and KeyLines. Just by way of introduction to kick things off, my name is Dan Williams. I'm the product manager for KeyLines here at Cambridge Intelligence. But all the hard work today is going to be done by my co-presenters. We have Brad Beebe from AWS and Christian Miles from Cambridge Intelligence. And you can read a little bit about them there, but they're going to be doing the bulk of the presentations and the demonstrations today. By way of agenda, the plan is we're going to start with Brad. He's going to give us an introduction to graph databases in general and Amazon Neptune in particular. And then Christian is going to move on to a case study for how to visualize graph data in Neptune, specifically for fraud analysis. And we'll then move on to the Q&A. So we expect about 45 minutes of presentations and demonstrations today, followed by the Q&A. And just as a reminder, we are recording the session. We will send a recording round probably next week. We'll put it together and send it out to all attendees. And the main thing is please submit your questions. So you are muted. We can't hear you, but we would like you to interact with us. So there is a panel where you can ask questions in the GoToWebinar. Please do, if you think of any questions for either our presenters, submit them on the GoToWebinar panel and we will answer those at the end. With that, I think that's all we have by way of introductions, so I'm going to hand over to Brad.
Hi, well, very pleased to speak to everybody today about Amazon Neptune. I'm Brad Beebe. I'm the product manager for Neptune. We built Neptune because what we saw was that customers increasingly needed to process what we think of as highly connected data. And this data is characterized by a couple of different things. It's produced very quickly by a number of different devices. It is heterogeneous in terms of its information type, so there's many different attributes and schemas involved. But most importantly, the value in processing this kind of data really comes from the kinds of relationships that the data expresses. And what we saw increasingly was people wanted and needed to build applications that process these relationships. So there's really 6 major use cases that we see for connected data. The first is social networking. I think this is generally well understood about how people are connected to each other, how they have shared interests, and these kinds of things. We also see various different types of recommendation applications. So these can range from product recommendations, what product should I recommend to you, to friendship and social recommendations, to things like in-game offer recommendations. Is there something that I can present to a player to help them change state and affect the change in their playing behavior? Knowledge graphs are a space that we've seen a lot of activity in, particularly over the last 12 to 18 months. And what knowledge graphs do is they use a graph model to model an information domain. And then based on that model, they do things like improve information retrieval, drive question answering systems, those types of use cases. Fraud, which we'll go into in more detail today, is a fairly classic graph use case. There's both real-time fraud detection. Should I process this transaction now? And there's also more retrospective type fraud use cases. Can I look longitudinally back over my data and try and find patterns of malicious behavior? The life sciences has a breadth of different use cases for graphs. These range from managing clinical trial information to drug hypothesis generation. How do I discover new treatments for existing approved drugs? To just data integration. How do I take many different medical systems that have different schemas and formats and give the treatment practitioners a canonical view over that data such that they can see all of the information when they're making treatment decisions. And then finally, networks themselves are fundamentally graphs. And so we see use cases in networks from protecting your network, what's going on at the edge of my network, to different types of capacity planning and simulation. How much capacity do I need to build? What would happen to my data center or power supply went out in a particular rack area? So there's just a breadth of different graph use cases. Let's go through a couple of examples. This is looking at a recommendation example. On your left, you'll see there's some shared interests, there's some product purchase, and then on your right, you'll see some social information. And you can use a very basic technique called triadic closure. A triangle is the smallest fully connected subgraph. And by trying to find these that you can complete in your graph, you can use that as the basis for a recommendation concept. And so we can say things like, you may want to purchase this product because people who also follow sports purchased it. Or you can do something similar in a social context, where you can say, recommend a friendship based on a shared friend that you have in common. We talked about knowledge graphs in general. This is an example taken from the World Wide Web Consortium, or the W3C's Knowledge Graph Primer. And we start with some information about artwork, artist, museum locations. So we have the Mona Lisa, Leonardo da Vinci, and the Louvre. And we're going to add some social information. So we have a small social network with some interest there. And we also have some geographic reference information. So where is the museum located? Where are places that these people have traveled? And when we bring all of that information together in a knowledge graph, we can start to answer questions like, who painted the Mona Lisa? Or what museum should Alice visit while in Paris? Or what artists have paintings in the Louvre? Amazon Neptune is currently in a preview, and we have a number of different participants in that preview, one of which is Thomson Reuters. And there you have quite an interesting use case. What they're doing is they're using a graph to model global tax policy regulations by geographic region. And then they also have models of their clients' corporate and legal entity structures. And they use those to help their customers both understand what are their tax compliance obligations, as well as to help them to optimize their overall tax posture. So quite an interesting use case. So when we started off, we asked ourselves, what are the options that customers have to process this kind of data? And the first natural question was, can I use a relational database to process graph data? And the answer was, well, yes, you can, but there's a couple of different drawbacks. The first is that the way that you write graph traversals in SQL is through join operations. And any sort of meaningful graph traversal very quickly becomes a large number of complex join operations, which is both difficult to manage and maintain, as well as slow to execute. The second thing that we found is that the kinds of I/O workloads that characterize relational databases are very different than what we see in graphs. And so graphs tend to have a large number of self-join operations, as well as lots of random I/O read access. So relational databases in general aren't optimized for the same kind of data access patterns as you get in graph databases. And then finally, one of the real strengths that we saw is that people were using graphs to relate data sets that they had no a priori concept that they wanted to bring together. And this was really some of the core power of their applications. But with relational databases, evolving schemas can be quite a complicated and challenging thing. So this was sort of the third area for relational databases. So we can also look at this from a data modeling perspective. On your left-hand side, you'll see a notional entity relationship diagram for a sort of a conceptual HR system. And this is purpose-built for a business process to perform HR for an organization. And there's lots of different valuable information that's stored in that. And it does its HR processes very well. But if you suddenly want to ask a different question, one that for which the data is not laid out or organized, then it's very difficult. So suppose I want to find out, what skills are required to build a particular product? Well, the data is inside of the HR system, but you're not able to ask a question like that. If you look at it from a graph model where the relationships become their own first-class objects in the data model, it's much easier to write traversals and to be able to express these kinds of patterns. So a graph database then is a database that's specifically optimized for the efficient storage and retrieval of highly connected or graph data. There's two major graph models and frameworks. The first is something called property graph, Property graphs consist of nodes and edges, and the nodes and edges both have attributes. There's an open source package called Apache Tinkerpop, which has a language called Gremlin that lets you write imperative traversals over a property graph. The second model is something that's a set of standards from the World Wide Web Consortium, or W3C. That's collectively known as the semantic web. It has a graph model that's called the Resource Description Framework, or RDF. And it also has a declarative graph query language for RDF, which is something that's called Sparkle. Whereas property graphs think of things in nodes and edges, RDF graphs tend to think of things in what they call triples, or a subject and a predicate and object. Well, in theory, you can do almost any application with either model. What we generally see is that people who are coming from a relational background and used to thinking of things in table structures find it quite a natural transition to think about nodes and properties and edges and edge properties. And also the imperative model that Gremlin provides can be quite a nice fit if your application itself is traversing the graph. And so if, for example, you think of a social networking application as a user interacts with the application, they're finding friends and doing and effectively building traversals, that can be a very natural fit for Gremlin. On the other hand, the RDF brings along with it a set of exchange standards. And so if you're using information that's already published in RDF, so for example, if you're using DBpedia or Wikidata, or if you're in the life sciences and you want to do things like chemical compounds or disease gene associations, there's a number of different publicly available data sets that are available in the RDF serialization. And so you're able to take advantage of those in your application. The other thing is that there's a number of related standards that go along with RDF to allow you to bring data together. So if your use case itself is data integration, that's a strength that customers find with RDF. So let's go through a very brief example. This is looking at a university, and it's an example taken from the Lehigh University benchmark, which is one of the sort of leading graph database benchmarks. And it has a generated university structure where universities have departments, and departments have professors and associate professors, and then there's students and graduate students, and professors take courses, and university and students, professors teach courses, and students take courses, and so on and so forth. And so there's a number of different questions here, but one of them that we want to ask is, can we author a graph pattern that says, find all the graduate students who received an undergraduate degree from the same university at which they're now doing their graduate work? And we could look at this as a graph pattern. If you look on your left, you'll see we're looking for graduate students that are members of departments, where those departments are organizations of the universities. Then we sort of close the join with where those graduate students also receive their undergraduate degree. So let's take a quick look at that and see how it looks in Gremlin. And so this is the Gremlin traversal from Apache Tinkerpop that would answer this question. So first we'd start off with graduate students, we'd traverse out to universities, and we'd find the departments in those universities, we'd find the graduate students, and then we'd go back and take the intersection. Now let's also look at it in Sparkle, the query language for RDF. And so here we see that across the top, that we're first looking for the typing information. We see that there's triple patterns here. And then finally, the last three statements, student, member of department, department, suborganization of university, and undergraduate degree from department, are where we actually execute the conjunctive join. And I'm not going to go into these in much detail today because we really want to focus on the fraud use case, but we wanted to give you an example of the ways that you can query this. So we looked around at some of the alternatives that customers have in this space about existing graph database options. And one of the things that really struck out to us is that we talked to a lot of customers that had had a very successful proof of concept or prototype with a graph database. So they tried out a system or a solution, they tried out for a particular application, and it worked really well for them. They found it was very natural to use graph query languages and APIs to express their problem, and they were able to get the performance that they wanted out of it. But they ran into challenges when they tried to put it into production. And the kinds of challenges that they encountered were they weren't able to maintain the query performance as the data scale increased. When they wanted to do things like configure high availability or encryption at rest, they found that these features weren't available in open source or community editions, and they needed to be licensed, which became quite expensive. And then finally, well, a number of alternatives do support both RDF and property graphs. There tends to be quite a strong performance bias, so that if you use a solution designed for property graph, you may be able to process RDF, but you'll accept a performance trade-off and vice versa. So with that sort of context, we built Neptune. And Neptune is designed to serve graph use cases that need to have query answering with very high throughput and low latency. And so we think about graph read operations in sort of two major categories. The first is what we call OLTP type reads. And we define these as parameterized graph traversals of less than 3 hops or parameterized graph patterns. And for these types of OLTP reads, the target throughput is to support up to 10,000 per server per second. And we support horizontal read scaling of up to 15 different read replicas. The second class that we think about are more analytic queries or OLAP queries. And for those, which we define as traversals of 3 or more hops, on-bound graph patterns, combinations of those, the target throughput is to support up to 100 per server per second. And again, supporting the same kinds of horizontal scaling. Now for analytic queries, the latency targets do vary, and they'll vary from hundreds of milliseconds all the way up to minutes, because the ability to effectively evaluate one of these very much depends on the shape of the data that you have underneath. So this will give you sort of a quick high-level architecture of Neptune. At the core of it is a purpose-built high-performance graph engine that's optimized for graph processing and is durable and ACID with immediate consistency. That is what interacts with the Tinkerpop and RDF Sparkle layer, where people are actually building applications. And then it rides on top of a cloud-native storage service. So this is technology that we share with other database services at AWS, and it provides us the ability to offer multi-availability zone high availability. So we store 6 copies of your data across 3 different availability zones, low latency read replicas. While the write master has immediate consistency, the read replicas have repeatable read with very low latency replication, so typically less than 10 milliseconds. And we support encryption at rest with customer managed or Amazon Key Management Service, KMS keys. And then in addition to the standard APIs that we support, we also have some additional things. So we provide a bulk load that allows you to execute a fast parallel bulk load by posting a JSON document to a REST endpoint, which specifies an S3 bucket and other configuration parameters. For property graphs, we support a CSV-based serialization in which nodes and node properties and edges and edge properties are serialized there. And for the RDF, we support 4 different RDF serializations. And so we support something called Turtle, N triples, N quads, RDF XML, as well as being able to allow you to provide a named graph URI as part of the configuration. So just to kind of recap the overall features of the service, you can see here all of the service is fully managed, so you can manage it via the console, SDKs, or APIs. We support the read replicas, high availability, things like backup and restore are all managed for you by the service. This is sort of a quick snapshot of customers that are participating in the preview. You can see we talked about Thomson Reuters, Siemens, AstraZeneca, FINRA, and Amazon Alexa are also participating. And then in terms of general availability, I mentioned that Neptune is in preview today. We're going to be moving towards GA very soon, most likely by the end of next month. That's going to expand from the existing US East Northern Virginia and add 3 additional regions, so US East Ohio, US West Oregon, and EU West Dublin. And then with that, let me go through and show you a very quick demo, and we can get to some of the visualization pieces. So what I have here is Amazon Cloud9. If you haven't used it, Cloud9 is a web-based IDE that you can use to develop applications. And it runs inside of your virtual private cloud, or your VPC, which is Amazon's sort of network security concept. And what I've have here is a sort of notional fraud example. One of the things that you see very commonly in fraud applications is this concept of fraud rings. And this is where individuals who are in fact colluding with each other go to one or more financial institutions and represent themselves to be independent individuals. And they then open various different accounts and financial instruments. And once those are opened, they'll execute various different schemes to defraud the financial institutions. And one of the ways that you can detect this is by looking for individuals that purport to be independent, but actually share common identification. And so people will do things like have shared national ID numbers or shared social security numbers. There'll be shared addresses and these kinds of things. So by looking for these kinds of fraud rings, it can give us an example or a place to start. Now, what I have here within Cloud9 is I have downloaded the Apache Tinkerpop Gremlin console, the 3.3.1 version that's available from the Tinkerpop site. I've made one minor configuration change here to put in the host name for my Neptune instance, which I've started within my VPC. And then once I've done that, I can go through and launch my console. And so here I'm just going to launch the Tinkerpop console. And the first thing that I'm going to do is ask my Tinkerpop console to connect to my Tinkerpop server. And to use that, I'm going to parameterize it with the remote YAML file that I customized for my Neptune instance. Then I'm going to tell the console to direct all of the input that I'm going to give it over to that remote server. And I'm going to go ahead and paste in this gremlin traversal. Now this traversal is going to look for fraud rings at any depth that exists in my graph. Let's see. I'll bring that up so you can see it. And so I've executed that traversal, and what I've found is these 5 individuals that are sharing identity information within the fraud ring. And so I've been able to process that, but as you can see, what I have is a nice textual representation, and now I want to look at how can we actually visualize this and help someone to really understand what may be going on. So with that, I'm going to switch back over to the KeyLines folks.
Thank you, Brad. Let me just share my screen. So this is Christian speaking. I work for Cambridge Intelligence. And my role with the company is to work with our customers across North America to help them understand and explore and discover KeyLines capabilities that allow visualizations against data sources such as the Amazon Neptune data source that Brad just showed. Our overall aim with our customers is to help them to deploy insightful and robust graph visualization applications. And today I'll be walking you through an example of one of those in particular. Now, we actually produce a JavaScript toolkit, and as a result, there's pretty much infinite possibilities for configuring the look and feel of the data that you feed to KeyLines. Our customers actually, they do really exciting things in a number of different domains, but today I'm going to be focusing on the use of KeyLines for fraud detection. Around 20% of our customers have deployed KeyLines to help triage and make sense of alerts that are generated by their innovative detection systems. This actually means that there are actually about tens of thousands of users, analysts, in fact, using graph visualization in this sort of way. Now, I'll be finishing my talk today with a brand new live demo of a dataset in KeyLines with similar characteristics to those used in fraud detection and investigation applications. And here's a quick look at that to give you an idea of what I mean by KeyLines graph visualization. Now, this is just a screenshot at this point. But the core part here is the KeyLines chart is here in the middle of the screen. Everything else on the screen around the chart has been developed by me to enable my users to interact with this visualization. So this is the graphical visualization, this interactive visualization at the center of the screen. It's often called a chart or a graph. It doesn't really matter which you call it. But what matters is it's interactive and intuitive to what you're looking at. And I'll walk through exactly what this is showing in a little bit. But one important thing to stress here is that, as I say, the way that the rest of this application looks is completely down to you. And that's just completely down to your designs and your end users and what you're looking to deploy. Now, before I move to the example, I'd like to walk you through 3 real use cases of KeyLines in the fraud domain to give you an idea of the depth of this use case. First up, we have a number of customers using KeyLines for visualizing alerts against insurance claims and policies. I previously worked for a company that does exactly this, and what they do is they do entity resolution. So they look at phone numbers across different policies and look at names and addresses and try to resolve where there are maybe pieces of collusion between individuals who are interacting with insurance companies. So, for example, if I had a suspicious pattern of accidents in my cars and it always happened over a certain amount of time, and there were other individuals in my network doing the same sort of thing, linked by these phone numbers or addresses, it may be something to look into. I mean, by definition, fraud is wrongful or criminal deception intended to result in financial or personal gain. So in this scenario, I'm looking to make claims against incidents that have happened. Maybe, let's say it's either premeditated, where I've planned it in advance. Maybe I've forced an accident, or maybe it's opportunistic. Maybe I've just decided because I've claimed against the windscreen in my car, I might as well also claim that important jewelry was stolen from the glove box. We have a number of customers who use KeyLines for credit card fraud visualization. One factor that's really important for credit card fraud visualization is the idea of geography. And we have a great mode that we call map mode to help people understand the connections across disparate geographical areas. Anyone who's had a credit card has probably heard of or received these texts themselves from their credit card company saying, we've detected a potentially fraudulent transaction on your account. Please give us a call and let us know if this is a correct transaction, this is actually you. KeyLines is often used in cases after that where you want to pick apart exactly what happened over time. What happened originally will be there'll be an instantaneous sort of alert that will maybe lock down the card. But after that, there will be an analyst ascribed to more complex cases to look at things in more detail and understand exactly which accounts were used and which merchants were used for different cards. So it's a really important part of that process for actually understanding what happened after the fact. And then finally, something that people don't really think of that often is the idea of a review fraud. So a lot of websites online, maybe websites for making recommendations for places to visit for eating or staying in accommodation. These websites really care about the reviews that are made on their website because it's effectively their IP. They want that information to be as truthful as possible, and it's quite important for them to make sure that they minimize any sort of fake reviews on the site as well. So KeyLines is used in that capacity as well. So using disparate data sources like IP addresses, as well as maybe looking at the actual text of the reviews that are being made and look for common patterns across those reviews. These all factor into maybe spotting instances where reviews are particularly incorrect or effectively fraudulent for personal gain for some reason. Now, about a year ago, I spotted this data set online. It's a really, really interesting data set. What it is, it's all cab journeys in New York City. There's some big CSVs on this website released by the government, and you can download them and you can have a look exactly where cabs were picked up, where they were dropped off, as well as some really interesting information about tips being made, the distances of the journeys being made, as well as the total of the journeys in terms of price of the full journey itself. I thought this was really, really interesting, and I thought it'd be a great use case to put the data into KeyLines. You have an implicit model there of people going from place to place. But one of the things about this was that there's an awful lot of data here. It goes back a number of years, and each of these CSVs you can download from the site are gigabytes in size. Fast forward to a few months ago, and I came across this article around a paper that was released. And I realized that this is a really great data set with some really interesting kind of sort of findings from this paper. And being introduced to Amazon Neptune, I thought it was a great opportunity to throw the data into Neptune and see how things could look using KeyLines. Now, what this paper shows is that it effectively posits or kind of suspects or highlights some sort of interesting activities. The idea here is that there's statistical significant patterns in the CAB data surrounding, in particular, the New York Federal Reserve Bank. In particular, there was potentially leaked communications around policy change events. So in a nutshell, around policy change events at the Fed, there was an interesting change in the flow of taxi cabs between the Fed and various restaurants and other locations. Now, those taxi rides could maybe be for a certain number of people. They could be to certain locations. And most importantly, I guess, it's at a particular time of day. So maybe around lunchtime to particular restaurants, or maybe late at night with a number of people from the Fed. Now, spoiler alert, I did put this data into Neptune and I queried it for the presentation in the KeyLines application that I've already given you a flavor of already. But there's no smoking gun here. I'm not going to be pointing at the data points and declaring fraud. It's quite interesting, as software vendors, it's not really our position to be pointing out fraud. What we're doing is we're providing the tooling to allow you to do the analysis yourself. And we can hand over the tools and the scalable databases and the innovative visualizations to the real experts who can make a judgment call in terms of whether something is fraudulent or not. So let me walk you through exactly what I did with this data. So as Brad inferred from his Cloud9 tool, firstly, I loaded my data into an S3 bucket here. So that's at the top left of this diagram. This was quite simple to do. I just had the basic CSVs effectively loaded exactly from the original site. I had to do a little bit of transformation to get into the right format, as I wanted to use Tinkerbell and Gremlin for my general querying and traversals. But once that was loaded into the bucket, I could then easily load it into Neptune with the bulk loader that Brad alluded to earlier as well. Now, the biggest part of this diagram is certainly the KeyLines logo here at the bottom. And there's also a number of other logos here for different frameworks that are optional for you to use with KeyLines. KeyLines is a pure JavaScript module, so there's no third-party dependencies. But you can use these frameworks if you are working in a large team and maybe have a stack preference. For the demo I'm showing you today, I'll be showing you from Vue, which is just something I've been interested in recently. But it's important to stress that it's completely down to you whether you want to use a framework at all. It can just help you with some of the UI elements of your application, as well as maybe your state management, which can be quite a complex thing to manage for intricate applications. So what happens here is I run queries from my KeyLines instance in the browser. My KeyLines application was deployed to EC2 for easy querying against my Neptune instance. And those query results were fed back to my application, and you'll see the visualizations that happened as a result. All in all, this took me less than a day to get set up. There were a few data issues on my side, but that was more just getting to grip with the data set. And as ever with this sort of project starting from scratch, you maybe go through a few iterations of a model. And data modeling when it comes to your graph is quite important. But what I'll show you today is that it's not the be all and end all. It can be the case that you can change your model on the fly to show different things in your KeyLines visualization. So what model did I set up on? Here's a quick view of a very, very simple model that I worked on. So at the far left here, we see a green icon showing that one person was picked up. This node here is representing a specific point in space. So I decided to use the lat-long coordinates provided in the dataset to derive points in space that would be nodes. And it's green and it has a 1 because it means that one person was picked up at this location. We have a line there, so that's what we call a link or a relationship. And that's showing that we're going from this location to another location. And then as a result of going there, we've also put the little text on these nodes to represent exactly the value of the fare, as well as any tip that was given as well. So clearly in this case, there was 0 tip given, which is probably maybe fair for the duration of the journey perhaps, but it's probably not too well received by the driver. But then in the middle, I've decided to put what we call a glyph on the link. I could have made the link width represent this number, but I quite like to see numbers quite often. So this number is showing me the duration or the distance of this cab journey. So it's showing me from this location to this location, it took 1.4 miles, and as a result, this much was paid. This sort of visualization can be an iterative process for making it look as you want. I've used font icons here in the background as well, so it's relatively quick to understand what's going on here. I can see a person, I can see a flag kind of indicating an endpoint. Colors are a really nice way of giving a kind of like quick segregation of those two types of points. And I went for yellow for the link just because I think it looks kind of nice for cab journeys, especially yellow cabs. But I often find these sort of visualizations can be subjective. People have different preferences, and it's very easy with KeyLines to change the way things look depending on your feedback or depending on what you're actually showing on the screen, maybe as a result of clicking around. So here's just a sneak peek before I show you the real application. This was an early model, and I used the same model I showed on the previous slide, and I used our map mode, our geospatial mode that I mentioned, and I'm able to plot those points in space right here in the real world. So this is still a graph, but it's now effectively in a layout that is representative of New York here. And that makes sense because of the layers of the map tiles that we have in the background. But I think this is actually a really interesting point I want to make, in that often when you start to visualize your data as a result of querying against the data set, you can see that there are maybe some patterns that weren't so obvious from just looking at it in its raw textual form. And the pattern that I immediately spotted that it didn't sit quite well with me or sit right with me was that there was an awful lot of red here in lower Manhattan, which didn't make any sense. So for this time period, why would all these cabs be dropping off in Manhattan but not being picked up? We see a lot of green all over the place otherwise, and you see red maybe further out, so people are going further out with their cab journeys, maybe returning home. So this was immediately a red flag to me in terms of either my model or in terms of my data set. And actually what happened is I used the green cabs in New York. If you've been to New York, you maybe know that there's sort of out of downtown cabs, there's the green cabs, and then there's yellow cabs, which can actually pick up in lower Manhattan. And that was the problem. I was using these green cabs, which meant that no pickups were being shown for this time period in lower Manhattan. And that actually works quite nicely because in many ways, insurance analysts and investigators go on a kind of gut feel from their expertise of maybe 20 years in the field or understanding how their cases in their particular domain work. So it kind of goes hand in hand. This sort of gut feeling from looking at this visualization and saying, hey, something's not quite right. That could be married with a fraud analyst, years of experience, to get quite a nice sort of environment for investigating these sorts of fraudulent cases. So let me jump to my real application without further ado. So here we saw this screenshot already, but this is now live in the browser. I've just put it into localhost for now, just so I can show it for this webinar. But right here we have our chart in its original form as I've loaded it. So to reiterate, I fed a query to Neptune. I actually chose to choose a particular day for this webinar, and I also chose just over the lunch hours to give you an idea of how you can filter down to a particular date range using my Gremlin query. Now in the browser, I can zoom in and out with my scroll wheel, so I can look at this large cluster here. I actually truncated a little bit artificially the lat long coordinates to give myself a bit of a cluster in terms of points in space. I didn't really want to have separate nodes for like a meter apart from you picking up a cab to me picking up a cab, as it kind of doesn't really make too much sense. And also you can kind of expect that there's maybe a little bit of fuzziness in terms of the GPS reporting. So that, as a result, that's the cluster that is showing here. That's this large cluster of people picking up and being dropped off at the same sort of location. As I zoomed in, you can see we have a nice little overview window here. This allows me to look at the overall network and see where I am in the network. And if I zoom over here and look at one of these routes here, these little journeys here, I can look at this one in particular. I see one person was picked up. I see the distance that was traveled, and I see the details of them being dropped off. Now, you can probably spot at the bottom of the screen here, I have what is known as the time bar. And this is another KeyLines component that works hand in hand with the KeyLines chart or graph. By selecting points in the chart, I can get a summary of those points in the KeyLines time bar. And just as a note, the time bar is currently showing me all the timestamps that are found on all these trips for the taxis, and it's aggregating them into this nice histogram format here. So I can see that in my data set, I get a drop off near the end, and that's actually as a result of my query. I've actually, because I've queried here, those durations of the cab rides mean that I'm not getting the pickups after this date here, or rather the drop offs after this bar here. But by selecting this link here, I can see exactly the duration of this transport. So I can see that this was the duration here between the end of 12 o'clock and early into 1 p.m. And I can do this and compare and contrast between different routes taken by different cabs. We can also do the vice versa. I can use the time bar and I can drill down into different time periods. And as a result, you'll see there that my chart is being filtered down, and I'm only showing things that are relevant to a particular time period of my current drill. If I force a new layout, which I can do at any time with KeyLines, I can now focus on that particular time period and spot exactly where the taxis were being picked up and dropped off in this sort of topological view. Now, if I go back to my full view here and run our layout again, I can get a clearer view again of that overall network with this data set. Again, I see that big cluster there as well. Now, by default here, I've set all my nodes to be the same size, they're uniform sizing. As part of KeyLines, we also have a graph engine that allows you to run algorithms right here in the browser. We don't need to go back to Neptune to get algorithm results. Instead, I can run algorithms right here in the browser to derive influence factors or other network characteristics that aren't quite so obvious by just looking at the chart like so. My demo here, I've put in a little widget here that runs this sort of algorithm, and I can scale my nodes by eigencentrality, which is just a fancy word for influence. By turning that on, we're actually going to resize those nodes to match the influence that they have. And in this sort of network, influence is really just a conduit for kind of popularity in some ways, or it's just giving us an idea of how in this large cluster, a lot of people are visiting effectively the same sorts of locations. So if I zoom in again, we could spot here, and I can select one of these to highlight just exactly that location for a drop-off, and I can get a breakdown again in my time bar for exactly what was happening over time for this node. Now, you'll recall from my earlier screenshot, this is just one view of the data. I'm just looking at things in a sort of topological, raw connected sense. What I can do with KeyLines is with a single line of code, I can view the same data in the geospatial domain that is kind of intrinsic to this data set. So by turning on map mode with a button here that simply calls map mode show, I can take the same data and I can plot it right there on a map. And my same functionality I've shown you so far is still possible. I can still filter down by a time period, like so. I can go down to a particular point in time, and the nodes on the screen are being filtered as such. I can zoom in and out as before, so I can focus on particular points, and you can start to spot maybe a bit of the rounding that I've done there. So you can see that those points in space are kind of rounded to this nice coordinates there. So that's why it's a little more geometric than maybe you'd expect. And I can still select nodes and maybe look at the different routes between different nodes and look at the timestamps of those as well, like so. Now, the logical next question when you're looking at this sort of data is that really this is a little overwhelming in the view. As an analyst, I don't really necessarily care to look at the whole data set here. Maybe I'm looking for a particular location of interest. Maybe I'm looking for a particular time of interest, and I've shown how I can filter that by time. But in terms of location, we have a great piece of functionality that we call combos or combining nodes. And this goes back to what I was saying about how you can change your model on the fly. Here, just because I've decided to create nodes as a result of points in space, here the geospatial points, doesn't mean that I can't decide to maybe group those nodes by the sort of effectively clustering it in real space in the world. So I've got a toggle here that will turn that on. If I turn on combine by zoom, what happens here is that depending on my zoom level, I'm going to combine my nodes as shown on the screen. So I'm going to group them together into the nodes you now see here. I'm also going to group together the links between those nodes. And I've added a nice little extra touch, which is a donut, as we call it. So this donut is showing me the breakdown of pickups and drop-offs for this location, for this sort of cluster around this location here on the screen. And you saw there, as I zoomed in, I get a nice change in my clustering. For a real-world application, it's likely that you want to cluster maybe around the New York Fed or maybe around restaurants of interest, depending on the paper. But here you can see, in principle, we can do it pretty much on any sort of grouping or clustering characteristic here as well. I really like this sort of view. I think it combines a few different things. Firstly, we have our raw numbers. We get an idea of the counts of taxis being picked up and dropped off in this location. I get a nice categorical view of those pickups and drop-offs. So I get a quick idea that, it's roughly half and half for downtown, whereas over here, more people are just being dropped off over here. I get my raw links, which have been bundled together with the width. So you can see the propensity of people to travel between different locations here as well. And then above all, I get a nice layout here that is showing me in real world. So it makes a lot of sense. Immediately looking at this, I see this is New York, and maybe if I've seen the map before, I'm quite familiar with it, and I can start to get to work with looking at my data set. So that's really all I wanted to show today. As you can see, there's a lot of characteristics here in this data set that are very similar to real world fraud data sets. One thing that we are missing here is definitely any sort of identifying characteristics. So I don't know who is taking cabs. And of course, that data set released by the government doesn't include that data. But I think that's a logical next step. If you were going to be using this in some sort of production environment, you would certainly want to know the real details about the people actually using these cabs and maybe following them over space and time, which is exactly what you can do with this visualization. So with that said, I will hand back over to, I believe, Dan. Thank you for your time, and I'm happy to answer any questions.
Okay, well, thank you very much to both the presenters, Brad and Christian. We're going to move on to the question and answer session now. So if you do have any questions for Brad or Christian, please send them in using the GoToWebinar question panel, and we'll do our best to get through as many as we can. We've had quite a lot already, so we'll get through them. We'll start working through them now. We had some questions in advance, but some questions live now. I think we'll start with the live ones. Live ones, one question is, will the recording be made available? And yes, we will be putting the recording together and sending it out probably about a week from now. There's a question which I can take, which is just, since Neptune isn't GA, how are people using KeyLines for fraud? I think maybe that's just a misunderstanding. So KeyLines and Neptune are separate products. So KeyLines is being used independently of Neptune, but today we've been showing you how they work together. So that's probably the answer to that one. Then we have a question. I think this question is probably for Christian and refers to what you showed in the demo. So the question is, when ingesting data, what tools are you using to convert the raw data into RDF and or property graph format? So I guess it's what tools did you use to get that data into Neptune in the demo you showed, Christian?
That's a great question, and of course, there's really a lot of different ways that you can do this. For the demo today, for my sins, I've just been using JavaScript and Node recently for sort of small conversion jobs like this. You can bash those up obviously by the command line, but that's exactly what I did today. For larger scale projects, for maybe more of a data analytics piece, I'd actually use Python, and it's quite nice to work with this sort of data. But really, in the property graph space as well as in the RDF space, there's definitely preferences for different sorts of tools, and we can maybe follow up afterwards in terms of what I'm seeing in the space being used. But really, I think the bottom line answer is whatever works for you, really. You want to get your data in the right form, and you often want to just play to your strength.
Great, thanks. So there's a couple of questions actually, all relating to scalability. One from in advance of the webinar and one just live now. So maybe I'll ask Brad first about Neptune specifically. At what scale has Neptune been tested? How much data can be ingested?
Yeah, so the distributed storage layer that I talked about earlier supports a storage segment size of up to 64 terabytes. And in our testing, that translates into graphs of somewhere between 100 billion and 200 billion nodes, edges, and properties, or triples if you're in the RDF space.
Okay, great. And before the webinar, there was a question, can these tools manage the analysis of graph data at scale? So I guess, Christian, I don't know if you have anything you wanted to add on the scalability from the visualization point of view.
Yeah, of course. The demo I showed today showed maybe a few thousand nodes and links on the screen, and it may be a little laggy on the conference, but it was quite smooth on my end. We have a WebGL renderer that means that we can get up to tens of thousands of nodes and links on the screen at any time. It uses the GPU in your computer to get the most performance out of the browser and about the client-side application. Our general suggestion is that really, if you're looking to visualize that sort of volume of data and maybe larger, it's a little overwhelming for end users, and there's definitely a limit in terms of human comprehension from looking at those screens. I think one of the final screens I showed you, there was an awful lot of data points. It made a little bit of sense because it's on a map, but if you were to really try and understand that, there's definitely a limit to the human comprehension. And then you should really look to your model and some of our capabilities to help cut down that data in the browser, like with the combos and the time bar that I showed you today.
Okay, great. One for Brad. I guess this is a question about the Neptune data model. So the question is, within Neptune, is data stored in a universal model so that the property graph is queryable through Sparkle, and conversely, RDF data can be queryable through Gremlin, or are they entirely independent? So maybe you could just clarify a little bit how the two different approaches work together and whether they're completely interchangeable.
So today, data that you load as RDF is only queryable via Sparkle, and data that you load in Property Graph is only traversable via Gremlin. That's a feature, not a technical limitation of Neptune, and so we are very interested in use cases that where you want to have data interoperability between RDF and property graph. There are some cases where there's some aspects of the modeling that needs to be resolved. So for example, if you're familiar with RDF, you'll know that to do statements about statements or edge property types of use cases, you need to do reification. And so there are some technical details about how that interoperability would need to work out, but we do have some ideas around it. And we are seeing a lot of customer use cases for it, and they generally fall in the category of people wanting to use RDF data to do data alignment, produce canonical models over data coming from different sources. And then once they've done that canonicalization, they want to use property graph models to produce APIs or do different kinds of analytics pieces. So, you know, if you have use cases for it, we would really very much like to hear them. And I think it's something that I would say kind of watch this space in the future. But today we do not have interoperability between them.
Okay, sounds good. The next question, this was one of the ones sent in advance. I think it applies to both of you. So let me ask Brad first of all. It may not be an easy question to answer, but it's a good one. How can one sell the value of graphs and graph visualization to management?
So I think it's a great question. You know, part of the product hypothesis for Neptune is that, you know, we really believe that far more people have a graph problem than really understand how to use a graph database or, you know, understand how to use graph APIs. And so what we really try and think about it is in terms of the kinds of challenges. And so, you know, when you want to, if your core application is really about traversing data and traversing relationships, you know, that's really when I think you have a much stronger case to say, you know, if I do this application another approach, we're very likely to hit performance limitations, or the languages and APIs that we need to do it are not very effective, and it's going to take us more time to do it. And so when you kind of lay out that argument from a capability perspective, it can be far more compelling than saying, hey, you know, graph is really, really cool and I want to try it out. So, you know, we definitely see that aspect of it. That being said, of course, we are all graph nerds and we do think graph is really cool, but, you know, we understand you know, that it's important to be able to make the case for, you know, when should I use graph processing versus another type of specialized database.
Thanks. And Christian, I don't know if you have anything to add from the visualization side on the business justification.
Yeah, one thing I've seen work quite well in the past, although it definitely is something that you need to take time to work out how you'd actually do, but I've worked with companies in the past who've taken a snapshot of their database at a previous point in time, and they've worked through cases using the new visualization tool, often KeyLines, and they look at the case and say, if I had looked at this case at that time with the tool that I have now, would I have made a different judgment? Would I have made a different call on maybe shutting down a case or shutting down a claim against a policy? And that's one of the few ways that you can maybe start to get a number out in terms of maybe how much money you could have saved by using a tool like KeyLines with Amazon Neptune as a backend. As I say, that would take a fair bit of investment of time, but it's certainly a way to get some concrete numbers in terms of maybe thinking about how this could have helped you in the past and how it can help you in the future.
That's good. Okay, this one I think is a Christian question. Which endpoint does KeyLines use to query? Can it be pointed at Sparkle endpoint, or does it only work on the property graph via Gremlin?
KeyLines doesn't really mind what sort of data it works with. For this demo, I just pointed at a Gremlin endpoint, but previously I've worked with Sparkle endpoints. There's a really lightweight JSON schema that KeyLines expects. Very, very simple. It's just a flat array of nodes and links. So really, whatever data form your data is in, you can work with it. But especially with Gremlin and Sparkle, for example, with Neptune, is perfectly reasonable, and a lot of our customers do that.
Right. And again, a KeyLines question: How can the graph analytics results from KeyLines be shared with other systems? Can it be done real time and automated? I guess maybe you could just say a few things about what people tend to do once they've generated the results in KeyLines and how it can be shared.
So the interesting thing about the KeyLines graph engine is that it's often just used as a sort of local analysis against what is locally loaded into the browser. So the data I showed you in the browser wasn't the full data set. It wasn't exactly what was full in Neptune. But that data, I did want to do some sort of analysis on it. I did want to get an idea of maybe influential points in that data set. So by running the KeyLines algorithms right there in the browser, I can get an idea of those importance factors in a way that makes sense to me because it's showing me as a result of the things that are in the screen right now. So what I'm saying is that is effectively a nice way to work with data in a subset to get an idea of understandable algorithm insights because I can see everything on the screen. But really for sort of heavy lifting, you want to turn back to Neptune or the graph algorithms to run things against your full corpus and maybe feed those back to you as a visualization element. Happy to take that offline in terms of how other customers are doing that, but I think it's a really nice way of showing some immediate results in terms of insights derived by algorithms in the browser.
Okay, sounds good. We got a couple more minutes left for questions, so I'll just get through as many as we can. Thanks for people sending them in. They're still coming, which is great. One question, the question says, I might have missed it, but how was data transported from S3 to Neptune? Do we need to build a scalable component for it, or does Neptune take care of reading it? Brad, you can comment on that.
Yeah, so the bulk loading interface that I referenced is the way that Neptune reads from S3. And so what you do is Neptune exposes a REST interface, and you post JSON documents to that REST interface where the JSON documents describe bulk load configuration. So they contain an S3 bucket, the parameters for the bulk load. One of those parameters is an assumed IAM role that you'd like the service to use to read from your bucket. And then it does a parallel load out of S3 into Neptune. Now, in terms of EMR, today, what you would do is essentially you'd have your EMR job write data to an S3 bucket, and then you would initiate a Neptune bulk load from that S3 bucket into Neptune.
Okay, great. And I think we've got time for one more, which there's a question, does Neptune have any features that handle timestamps?
Today, we don't have a particular features built in for timestamping. It is something that we're looking at in the future. Those kinds of use cases also come up in terms of time to live type cases, as well as security pieces.
Great. Okay. So thanks. We are out of time. So if you've asked a question and we didn't get around to it, we will follow up with you afterwards. We have your login information, so we'll be able to get back to you on those. But we are out of time. So just remains for me to say thank you very much to our presenters, Brad and Christian, and thanks very much to all the attendees for joining us, for asking so many questions. That's fantastic. And we will see you again at another KeyLines webinar soon. Thank you.